Welcome to the engineering station. I'm driving along a familiar route. My technical radar immediately detects a plastic module casually discarded. Approaching the target, this is the housing cover of a vertical blender. A scenario for diagnosing and repairing microchip hardware was immediately drafted in my head. However, we need to search for the motor core containing the main circuit board, maintaining speed on the mountain paths, and paying special attention to the outer edge. The drive systems of these devices usually fail at the control board. Entering the waste material gathering area with a high concentration of smoke from burning trash, analytical senses show that this place has an extremely dense concentration of faulty components. I decided to set up a field survey at the most detailed level. Moving close to the ecological belt of the scrapyard, it's covered in thick smoke. From an expert's perspective, this is a massive passive component gold mine. The chaos of thousands of discarded household appliances unfolds right before my eyes. Surveying along the edge of the cliff, my visual system continuously scans the surfaces. And there it is, a universal motor assembly has entered my analytical crosshairs, carefully approaching the edge of the slope to retrieve the base housing containing the motor. The outer ABS polymer shell still retains its structural rigidity without thermal deformation. Proceeding with modularization, the two physical interlocking joints align perfectly. Compatibility confirmed full recovery of the frame. The next step is to bring the device back to the lab, securing the device on the vehicle floor, optimizing the transport process to avoid vibration. Starting the engine, I leave the polluted area to head to the diagnostic station. The blender's universal motor has high torque, but often suffers from microchip hardware failures or risks. Can also come from physical breakage in the AC power sources. Navigating through the forest road, the device is kept perfectly intact before any intervention. Finally, landing at an open outdoor space, which helps solvents evaporate easily. Proceeding to lay out an anti-static workbench with a heavy-duty industrial plastic basket, setting up a standard ergonomic working position, and optimizing the viewing angle to inspect the circuit board, placing the device on the workbench to visually inspect the exterior surface before opening it up, detaching the cover, exposing the rotary clutch connected directly to the inner steel rotor shaft. I open the technical toolkit, which stores all the micro hardware intervention tools. The toolkit layout is quite neat. You'll need a standard Phillips head screwdriver, grabbing a mechanical tool with magnetic torque to easily attract and remove the base plate screws, breaking the compressive force of the first. Screw at the bottom of the heatsink plate, the thread. Grip is still quite tight. The cross-corner circular unscrewing technique prevents the plastic shell from cracking due to compression imbalance. Moving the pivot point to remove the second anchor of the motor housing's protective structure, taking out the screws and placing them in the magnetic storage tray to manage the risk of losing components. Approaching the screw in the third quadrant, dirt is stuck to it, but it doesn't cause thread rust. Finishing the extraction of the last screw, the physical latch securing the motor assembly has opened. The entire anchoring system has been isolated. Now, the plastic latch structure is the pressing factor. Using hand force to pry off the bottom flange, revealing the aerodynamic mesh slot heatsink design, the central core block is now exposed. An alternating current motor assembly, a classic AC universal motor, gripping straight onto the stator steel core. I gently pull the entire motor system out of the protective plastic shell, detaching the button board switch assembly, the control brain routing through the inductors. Observing the copper wire network and carbon brushes, the physical structure shows no signs of localized short-circuiting. To measure the microparameters, I proceed to access the specialized tools inside the toolkit box, taking out a high-current backup power cable, may be needed for the load error replacement process. The core diagnostic weapon right now is the accurate digital multimeter DMM. Unwind the anti-interference probe wires to prepare for supplying the test current. DC to check the circuit connection. Precisely plug the banana jacks, positive and negative terminals into the correct COM and V4 ports. Set the selector dial to continuous continuity test mode with the integrated buzzer alarm. Quickly short the two metal probe tips. Together, the system will signal a 0-ohm resistance range. Proceed to place the probe on the carbon brush connecting pin and the rotor commutator to check for voltage drop. The DMM screen returns a stable resistance value, confirming the stator winding is not broken or open. Move the measurement point to the multi-level mechanical switch circuit, where voltage routing changes the speed. Continuously press and release to simulate input, measuring the elastic switching pulses of the copper contact leaf. Review the internal power, supply transmission network, from the source rectifier block through the distribution system. Immediately detected a fatal hardware fragmentation error at the corner of the switch cluster. The copper traces have completely peeled off the solder joint contact pads on the printed circuit board surface, initiating the microcircuit soldering intervention process. I set up the digital thermal pulse soldering iron. The heating controller pushes the tip to 380 degrees Celsius, the optimal threshold to melt the tin alloy. Plug in the AC power, then dip the soldering tip into the Rosen flux solution to remove adhering oxidation. Accurately position the copper core onto the pad and apply the iron tip holding molten tin to the open joint. A technique of pulling and releasing the shiny tin cone will maximize the cross-sectional conductive area of the load electrons. Hold the physical structure steady for 3 seconds. For the tin-lead alloy to solidify with a strong microstructure, the solder joint is perfectly fused, with no cold solder joint phenomenon. The control board is restored. Unplug the thermal soldering system's power plug. The intervention process closes. The circuit is successfully fixed for step 1. Following maintenance standards, a cross-check step must be performed using the DMM. Poke the DMM probe tips into the 2 poles of the newly reinforced connection to verify if the contact resistance range has any gaps. The buzzer sounds, indicating the resistance parameter approaches 0. The transmission signal through the switch is fully continuous. Put away the measuring equipment and switch to analyzing peripheral errors. Inspecting the transmission loss of the AC power cable, detected material fatigue, the PVC. Sheath is crushed, exposing bare copper cores directly to short-circuiting with a very high risk of arcing. The solution? Cutting off the degraded element is a safety imperative. Firmly apply cutting force to eliminate this mechanically weak cable connector from the circuit. Separate the discarded components. We will extract the supply directly from the internal copper core wires inside. Make a sharp second cut to create a standard flat contact surface for the cable stripping stage. Lightly score the cutting blade around the main PVC protective sheath, applying braking force to avoid breaking the soft copper core. Pull off the thick insulating sheath, freeing the 2 internal power cable signal lines, blue and brown. Continue stripping the polymer sheath of each independent polarized phase core, exposing the bundles of pure copper conductive strands. Tightly twist the tiny thin copper strands together, condensing the mass for electron transmission to reduce electrical sparking, the natural biological sounds of the environment. Add to the authenticity of the makeshift workshop. Perform an equivalent twisting structural step for the signal pole of the brown phase cable. The shaped wire bundles. Initiate a standby. Module point right on the motor's direct power cable. This input wire also needs its insulation stripped, peeling the insulation off the input cable section to prepare the surface for the Western Union's straight splice technique. Access the toolbox to grab the roll of PVC tape. Specialized for low voltage insulation, an essential material to protect the circuit. Braid and twist the copper wire bundles into a cylindrical cone connection. Pressing force creates an absolute physical contact area. The tightness of the twist will eliminate phantom impedance, preventing voltage drop issues when the magnetic disc rotates. Wrap the electrical tape tightly. The elastic force stretches the tape, and the adhesive will activate its absolute chemical bonding. Repeat the cross-twisting and taping process, ensuring electrical safety for reverse phase transmissions. Press the tape edges to completely seal any gaps, blocking moisture from the environment that oxidizes and rusts the copper crystals. The final blocking step. wrap a single piece of electrical tape covering both joints, preventing mechanical strain and cable bending. The splicing technique for the main power cable is now complete. The electrical safety margin for AC current is extremely high. Further analyzing the wall plug, the metal pins are covered in rust and residue. I am discarding this aging component. The plug assembly causes interference, eliminating the root cause of electrical arcing. When plugged into the wall outlet, the electrical circuit is balanced, ready to activate the module. Mechanical cleaning with a bristle brush sweeps away hard, dry dust. Brush out the cooling slots at the bottom of the base to maximize airflow cooling. Remove the thick layer of spiderweb stuck in the plastic crevices, preventing friction on the centrifugal rotor shaft. Clean up the accumulated dirt in the corner positioning slots. A sterile environment will extend the aging cycle of the stator. The cleaning maintenance step is complete. We are moving on to the reverse step, reverse engineering assembly. Drop the control button circuit board to slide along the fixed tabs, requiring millimeter precision to align the screw holes. Align and fine-tune the physical buttons, pressing them to test the key travel range, ensuring a bouncy touch without rubbing against the side edges. Lower the heavy central motor assembly onto the anti-vibration anchor points, the rubber damping mounts. Organize the wiring layout for cable management, route and clip the cables to prevent the compartment dividers from severing the bundle. Snap the bottom heat sink cover back on, position the plastic locking ring, snapping it tightly into the main mechanical frame. Use a screwdriver to lock the threads, securing the compressive housing frame. The twisting force must be firm to sink the iron screws into the holes. Apply the cross-screwing principle to distribute the compressive pressure evenly, preventing the core plastic edges from warping. The final thread lock on the base. Cover is tightened, restraining the high-frequency vibration of the oscillating machine. The core is completely sealed. Flip the machine assembly over and test fit the blender module. Pitcher and lid onto the rotor base, ensuring the clutch wheel connects securely. Exterior refurbishment and polishing. The standard step in the surface aesthetic recovery process. Cosmetic rework of the device. A microfiber cloth scrubs away calcified chemical residue and pollution, restoring the glossy finish of its industrial design. Set up a load stress test, applying a 220 V current at max RPM. The motor runs perfectly at maximum speed with no arcing. Turn off the power and discharge any residual current. Move on to packing up the workstation. Fold up the toolkit box and put away the specialized measurement devices. Latch the toolbox shut. The process of reviving a piece of hardware trash is a complete success. Diagnosing and repairing hardware components is truly an art form.